shortest job first. Okay, that is the shortest job first. We can select the process that has the rest, the minimum, the CPU burst time. So, however, we talk about the two types of the scheduling. One is preemptive, the other one is non-preemptive. In operating system, if you encounter the name of a preemptive or non-preemptive, so we will see the one more time, the several times in the other operating system algorithm, like the for example the deadlock. So we will see the what is the non-preemptive and the preemptive. If we see the name of the preemptive, means it can be resumable, so we can restart later. On the other hand, the non-preemptive means we cannot restart, which means once the process, any resources start, it should be done, terminated. So if we consider the non-preemptive, the shortest job first, that is the CPU burst time. Okay, but if we think about the preemptive, so whenever there are events like the interrupt or the terminate or the wait or the, we talk about such different cases of the event. At that time, so if we reschedule, that is the preemptive. So preemptive version of the shortest job first means we are going to consider remaining job. So shortest remaining job first is the preemptive version of shortest job first. Okay, at that time we can consider the remaining CPU burst time as a priority. Then another one is we can just explicitly assign the priority number. So lower number means the higher priority. For example, Windows uses 0 to 31, the different level of a priority number. Unix system uses also such a priority-based algorithm. It's a nice number. So if you see the nice number, NIC, that is the same as a priority number. So we can consider. The problem is, how can we assign the priority? So we can just divide into two groups, like the system processes, which will be started during the booting. They will have the higher priority. The others are the application program, the processes. So it will be normal process. But it's not easy even to divide into the which one is the system, which one is the application. So to address such a problem, we can consider different level of the queue. Instead of one ready queue, we can consider different level of the queue. Then such a multi-level, the CPU scheduling algorithm, we can divide the characteristic, the processes by the characteristic. Even how do we decide such a different characteristic? If we know, if we explicitly classify which this is a system process, this is a user process, it will be okay, but not always it is doable. Instead, why don't we consider the feedback of each level, so which is the multi-level feedback queue. So first one is round robin with a short amount of time, short the quantum size. Then it will be quickly assigned, but if that requires the longer CPU burst time, it will move to the next level. Next queue has the little bit longer quantum size, and so on. The last one is eventually first come first serve. So it's a multi-level feedback queue. So multi-level feedback queue considering the CPU burst time. So for example, how do we know CPU burst time? We don't know actually. We cannot see the future. Okay, nobody can assign this process require the 10 CPU time. No. Instead, we need to estimate. So for that estimation, the exponential average we can use. It's based on the previous one. We can optimize the tau value, the current and the previous. So it will be eventually very similar as we expect, but not always the correct. So if we are using multi-level feedback queue, no matter what size of the CPU burst time you need, it will be eventually moved to the next, and finally, using the first come first, it will be completed, terminated. It's okay, but it is complex. Think about how many times we need the CPU scheduling algorithm. It's a lot, really a lot. Okay, it's a millisecond level. So whenever we have the CPU scheduling, it also requires context switch, changing to the next process. It's overhead. So as we have seen in the process file system, or the top command, or the many, there exists a lot of such a monitoring the command. So if you are using such a command, or you can directly go to the root slash the ID number, so you can find the number of context switch. So even the normal process has the 100 times per the minute of the such a context switch. So if we have the very complex, the high complexity, the CPU scheduling algorithm, it will be overhead. So which means reduce the performance of your operating system. Okay, that's the overall thing that we have discussed regarding to the CPU scheduling. What we missed the last time is real-time CPU scheduling algorithm. Nowadays, it's getting the more important. There's such a real-time operating system. One common mistake is the real-time. Does not mean that it's really fast. Actually, ideally, is it possible really real-time? So it doesn't make sense. So anyway, we need such a latency. So latency means the delay of the time. So we have the two types of latency. Interrupt. So interrupt is a signal because we need to share the resource, especially CPU resource. The hardware or software raise their hand. I'd like to use stop, freeze, then I'd like to use the CPU resource. Then the scheduler assign another process or this process. But there might be something time in between. The signal, the interrupt, then restart. That is the interrupt latency. Then the dispatch latency means it will take a time for CPU scheduler to select another process. So that is the complexity. Depends on the complexity of the CPU scheduling algorithm. There is a slightly delay the time. That is the dispatch latency. Because of this, the interrupt latency and dispatch latency, anyway, it is not possible really real time. Instead, almost near real time. So that is our target. Also, when we define the real-time operating system, so you heard about the real-time operating system. Real-time operating system mostly require real-time CPU scheduling algorithm. Okay, not only just the fast hardware or the network, but the more important thing is the real-time CPU scheduling algorithm. So we talk about the two types of the real-time, the real-time system. Software real-time is other. So from that concept, we can define real-time, the system as guaranteed time. Okay, so there might be policy. For example, my alarm system, the fire alarm should work within 10 seconds. Then if that works, so we have a time to be evacuated. So that is the real time. If the fire alarm doesn't work within the 10 seconds, then it will be the problem. That is a real-time system. Okay, think about the nuclear plant in the Fukushima during the tsunami. So it should work within an hour. That is a real-time system. Okay, from that point of view, there are two types of systems. Software real-time means try, but we cannot guarantee. Many of the real-time system is software real-time. Okay, who knows? Even though we are executing the same program under the same environment, it takes different times. Okay, so we pursue such the real time, but not guaranteed always. But we pursue. On the other hand, if this operating system is used for such a nuclear power plant or very critical system, it must work. That is a hard real-time system. Nowadays, we need like the robot, the controller should be the hard real time, otherwise it will be messed up on the factory and so on. So we will see the two the basic real time scheduling algorithms. To do that, in the real time operating system, we define the periodic. Periodic means this is the CPU time, the computer time. So you can think about the human perception time, but this time will be divided into certain fixed amount of time, which is called the period. So within that periodic time, each job had required time t. So this is the CPU burst time. So instead, unlike the CPU scheduling algorithm that we have discussed before, that is the overall, the one process requires the 100, the CPU burst time. So it can be divided into several jobs, but as long as each process gets 100 CPU time, it will be terminated. However, in the real-time operating system, we divide the time by certain period, that is a period. Within that period, so the process requires time t. Okay? That time t should be done within time d. D represents the deadline. Within the deadline, within the guaranteed time, this one should work. Think about the fire alarm. Fire alarm, it looks like the monitoring 24 hours is without. So instead, every 10 seconds it check. Okay? Then checking whether there's a fire or smoke, so that require the 2 milliseconds. But that should be done within 5 milliseconds. So within 10 is one time slot, the period. Okay? Within that period, the process should work. Then keep checking, keep checking. Think about if one process is taking all the CPU time, the other, like the other process, cannot get the CPU resource. Because of that, in the real time, the operating system, we consider such a period. So this is obviously the time t CPU version within the period should be less than the otherwise it will not be real time. It cannot guarantee. So then this deadline should be less than the period. So from that point of view, the first one is rate monotonic scheduling algorithm. So which means, so let's think about the two processes, the P1 and P2. P1, its period is 50. So it's and on the other hand, the P2 is 100. So P1 is more critical, right? It should work every 50 milliseconds. On the other hand, the P2 will be running every 100 milliseconds, which means P1 is more critical. Then we can consider the P1 has the higher priority, right? So then if we consider such a inverse of the period as the priority, then we can select from the reticule. This time we have the P1 and P2. Which one is more important? P1 is more important. So P1 will be selected. Then the P2. Then at this time the P1, the 50, the P1 is selected because the P1 has a higher priority. Then the P2, because the P2 need 35. Let's say the 35 for the time t. So this will not be completed, terminated, because P1 is started in this second period. So P1 will be selected. Okay. Then once the P1 is done, the P2 will be resumed like this. Then this one guaranteed. The P1 and P2 both process are guaranteed to be executed within its period. P1 is in the 50, P1 50, P1 50. P2 will be done within 100, P2 will be done within 100. Okay? This is priority based, but the priority is inverse of such a period of that. So shorter period means it's more critical, and longer period is less critical. Problem of this one is sometimes it can miss the deadline. For example, even though we have enough time, think about let's reduce the period of P2 as 80. Okay, so P1 should be done within the 50, so it's done. Then the P2 will be the next one. So it will take this one, this time P1's the so it's a 50. This is a period, this is time t, and P2 is the 25, 35. And this is at this time 80. Okay. So if we consider the priority as the inverse of a period, then the P1 is the more important. So P1 has a higher priority. This will be selected. Once this one is done, 25, the other 25 will be next process is a P2. So, however, once the new period of the P1 starts, the P1 will be selected because P1 has the higher priority. At this one, then the P2 cannot meet the deadline because this time the 75, it has only 5. So, however, if we change this is a 50, time 50, and the 60, 70, 80, 90, 100. At this time, the due of P1 is here. And this is the due of the P2. If we select the P2 first, that means this one, then the P1 can take the 25. 25, both of them can meet the deadline. However, if we strictly apply the priority of the process, we cannot meet the deadline. So to address such a simple the rate monitoring scheduling algorithm, so we can consider the earliest deadline. Which one should be done within the period deadline. So for example, in this case, even though the new period is started, we need to check which one has the earliest deadline at time 50. At the time 50, P2 will be the first one, then followed by the P1. So we can select the P2, which is the earliest deadline, and assign. This is a very, very generic, the real-time, the scheduling algorithm. There are a lot, so much more complicated. But if you have a very complicated CPU scheduling algorithm, overall performance will be slow due to the latency. So you need to think about the trade-off, such as the complexity of your CPU scheduling algorithm and overall CPU's your operating system algorithm. So there are, if you can find the published paper regarding to the scheduling nowadays, a lot of very domain-specific real-time the scheduling algorithm, like the robotics or such a power plant and embedded system. Then these two are the very basic, generic, the real-time scheduling algorithm. Okay, then we have seen the last time the example of the other operating system. Any questions? So our midterm will cover for those who were late today. So our midterm exam will be October 17, Wednesday in the classroom. We do not have class October 15, Monday, which is the fall break. So, but some of the professors will make up the classes, which is the one-day class, like either Monday or the Tuesday, but our class is the 2-day class a week, so I'm not going to make up. Instead, I'm going to give you the time for studying your midterm exam. That will cover the chapter 1 through 6. Hopefully, I will finish. I'm going to try to finish the chapter 5. In case I cannot cover the entire topic of the process synchronization automatically, which I couldn't cover, the contents that will be eliminated from the scope of the midterm exam. Okay, process synchronization. Anyone who ever heard about the synchronization problem in the programming class or any other computer science class? You should. So, A couple of years ago, I had a chance to have a lunch with anyone who ever used Priceline.com when you book the trip or the. What is the difference Priceline.com and the other? Priceline.com usually, I'd like to have you can post the trip, then the agent or the can bid for your travel, then you can select the cheapest one. That's slightly different from the other, the Cpdc.com or the what else, Trivago or whatever. Yeah. The other, the travel agent usually you guys can select the cheapest one among the list, but the Priceline.com actually the agent, travel agent can bid for your trip. But nowadays it's changed. A lot changed. It's almost similar, same. Because that works when we do not have many such a travel agent or such a website. But nowadays it's almost we are able to find the cheapest one by searching all the travel agents and so on. Anyway, Priceline.com is still one of the popular website to book a trip, but I had a chance to have a lunch with the CTO of the Priceline. Then, at the time, one of the professor who joined the lunch asked, when you hire the new employee, usually what is the most frequent asked interview question? Then he said his answer is, he'd like to hire the person who knows the synchronization problem. So then what is the synchronization problem? Why he from the Priceline.com consider the synchronization issues? Anyone? Synchronization.
It should be lifetime or
lifetime. Like synchronization means, so my daughter they just moved in this fall, then her roommate is a synchronized swimming team.
Okay, it's like to be unified, to move.
Yes,
to
it
move
should be the same, synchronized along the what? Always we have many processes, right? So we don't want something conflict situation. We don't want something the non-consistent data. Okay, it should be synchronized. We need to guarantee such the consistency of the data and the support of concurrency. So synchronization problem. Think about the Priceline data. So actually, Priceline they do not have the ticket, right? Mm-hmm. They do not own the transportation. Instead, Priceline.com has a lot of
redirect.
Right? So this is the MTA, and this is the Delta Airport, and how many the airline company? So many. And this one is the cruise, and this one is other. So many different, and their source their communication protocol are really variety. This one uses just the client and server. Some of them use the old-fashioned message queue and so on. Then eventually they will update their information to the certain database. Okay. Then the user would like to search like the trip from New York to the LA. And problem. Every time, every moment, they are updating, they are changing, they are accessing the same data. So if this user already either this agent read this data flat, but it's still available. While this agent is searching their data, the other agent, this user select the other agent. So this is done. But when I go back, this agent, so I found this one, the $1,000 update, but this one cannot get this one. So how can we guarantee? How can we synchronize this one? So this is the main problem of this. So this one happened in the application program. This one happened operating system. So we are going to take a look at such a synchronization issue from the operating system point of view. However, this one nowadays required in your application program. So I'd like to introduce in the application program level how we can address such a problem. Let's simplify the synchronization issue. So then, if you go to the dormitory, probably in your common room area, lounge, there might be bulletin board, right? Yes? No? Probably you have a bulletin board. So we'd like to have a party, not party. So watch the baseball game. So right now the Red Sox and the New York Yankees. So we'd like to have, so please put your name. Who wanna take the trip or this one? To the Boston or the Yankees. This is a shared data. Okay? Shared by many the student. So if this guy read there is a data A, okay? Data A, for example. Doesn't matter what kind of data, it's a shared data. So A. But this user would like to change A to B. So I'd like to put my name. Okay? I'd like to put my name to Trevor. So however, at the same time the user 1, user 2 would like to put their name, to update this data. Then this one, get the takeout, this shared data, the posting, then update A to B, A and B. Why this user is updating this data, the other user cannot access this data. So if we leave, so just read the data A, then update B. So it's A, B. But at the same time, if we do not allow, take out the posting, another user. So it's A, this user would like to add another data, A to C. Then, what will be the output? AB or the AC? Or ABC? You cannot guarantee the output. So we'd like to guarantee such an output that is the synchronization problem. So let me change the example of this one with the operating system. In the operating system, so we have the dual core. So this is a core number 1, this is a core number 2. So we have the memory. In the memory, the integer I value is 5. Okay? So the core number 1 is would write add. This one is the minus. So this one is a +1, this is a -1. Subtract the decrement or increment. Increment, INC. Decrement -1. So +1 and -1. So if both of them are executed at the same time, what will be the output of this? If the core 1 read I and the +1, it will be 6. Then followed by core 2, it will be 5. -1, so it will be 5. However, if this one is executed first, it will be 4, then +1, still 5. Unfortunately, both of them are read the I same time. Okay? But core 1, number 1, write the new data by 6. Then followed by this. That will be 4. On the other hand, this one write the 4 first. And followed by this. It will be 6. So there are 3 different possibilities. It can be 4, it can be 5, it can be 6. So That is the problem of the synchronization. We are saying this system is not synchronized. We cannot guarantee the output. So, such a synchronization problem will be happen. This condition is called the race condition. Race condition means a number of process, multiple process, concurrent system. So if you already took the database, you talk about the concurrency, consistency, or multiple transaction. Mostly, the computer system nowadays support multiple user. In terms of operating system, multiple processing. When we have the multiple process for the shared data, if this one is not shared data, like the post-it, take out the post-it and update and put it back. It's not shared. So when you use that data, it will be actually locked. But if you have the shared data, then the output of the process operation, we cannot guarantee. That is the synchronization problem. That situation is called the race condition. Race condition means the multiple process are accessing the same data, shared data. So because of race condition, we have the synchronization problem. So we'd like to address that problem. So that is the process synchronization. There are different solutions in the synchronization. Some of them are hardware level. The hardware level, when we are talking about the hardware level, hardware solution in operating system, means what? It's the instruction level. Instruction part, the operating system cannot modify or revise, touch the instruction level. Instruction will be provided by manufacturer of your CPU. So it's the hardware level solution. Sometimes the CPU processor manufacturer like the Intel and what else? The AMD, they provide a specific instruction to address the problem of the synchronization. That is a hardware level solution. Another solution is software level. Means in your program. In your program, you can address such a problem. One of the solutions is actually this one, lock. You can lock the data, but you can imagine if you lock the data, share the data, what happens?
Nobody can.
It's waiting. The performance will be degraded. So that is the software solution. We always see such a solution. But in the future, probably you need to use such a software solution. Who provides such a software solution? Programming language. Program language provide a library so to address the problem of the synchronization. There are operating system solutions. So operating system solution means operating system provide system library, specific system library to address this problem. Idea of regardless of the type of solution, we don't discuss yet what is the solution. Idea is lock. No way actually, but how to use such a lock. It should be fair. Okay, so we will define what is the requirement of the synchronization problem. Then we will see the solution, how to address the synchronization problem from the software, operating system, software, and hardware, and so on. So first, race condition means when multiple processes are accessing the shared data at the time it has the problem. So to address such a race condition problem, we need to synchronize the multiple processes. That is the synchronization solution. To do that, if you are studying any subject of computer science, so always we are. So what is the main objective of computer science? We try to solve the problem. It's real-life problem. Sometimes a specific, domain-specific problem. But anyway, to solve any types of problem, we'd like to use computer research. Okay. Then to use the computer research, we need to have the operating system, the program language, and the algorithm, and so on. At that time, many of the time, we are going to model the problem. Okay. In terms of computer science data structure. So such a modeling. So it's a very high level, though we are going to model the computer science problem. One of the popular is you probably use producer and consumer the problem. So producer and consumer problem is there's one process who can create the data. There's another process that can use the data. What is the typical example of the producer and consumer problem? Client server, socket program. Client requests the data, and the server receives that request and return back. So client server is one of the typical problem as the producer and consumer problem. So, I do not actually use only this modeling, but if you read the textbook use a lot of such the model of the computer science problem. One of the typical example is the producer and consumer problem. Another popular modeling is readers and writers problem. So we can consider the process, any types of the computer, the science, the job or problem as the readers and writers. Database user lot. The readers means
That's right.
there are two types of the process, readers and writers. So readers read the data. So no problem, but because of writers when writers write the data, at the time if the readers read, how can we read the data? Whether before or after and so on. So writers is another typical problem model. So we are going to use the producer and consumer problem to understand this one. There are many others. I will introduce later, maybe next class, the readers, writers, and philosopher problem, and the several. So we are going to use the producer and the consumer. The main part is the producer is writing the data for the limited buffer, and on the other hand, the consumer read the data from the buffer or share the data. So that caused the problem. So we have the readers, producer and consumer. And we have the shared data. So we can model synchronization problem using producer and consumer, the model. Okay. Then we will understand the race condition in terms of the producer and the consumer. So let's say the producer is the one process is plus and the other one is minus. So exactly the same example as this one that I introduced, but using the instruction. So you can see the instruction level, like the counter, the register, the increment, and the move, the write the data. Counter minus means is the decrement. Okay, so it has the three operation, three instruction. Okay, then what happened? Output maybe the 5, it can be 6, it can be 4. So this one, case 1, it will be first time read the 5 and read another process read the 5 and the increment is a 6. Okay, then the decrement is a 4 and the write back this one and the write back, so it will be 4. And or it can be 6 or it can be 5. So which means this, if we run as it is, it's not synchronized. So we need to address this problem. Synchronization means the two processes are synchronized. So in other words, the operating system consider two processes as a group. But if operating system does not consider such a thing, we cannot guarantee the output. If you already took the database class, how does the database address the synchronization problem? Anyone? Log. Yes. But there are a bunch of different levels of log as you learn. We can say actually most of solution as a log. But more specifically, database use transaction. So transaction means, since in this case operating system allow, so for example here, this is a count increment, but increment require how many instruction? 3 instruction. So and decrement require 3 instruction. Each instruction is atomic. It cannot be divided, split. However, if we allow interleave like the load 1 first, and this load second, and the increment third and the first, then it will cause the problem. So database consider group of operation as one atomic transaction, or nothing. If this one is started, and this should be the atomic transaction, group of the operation. So database use the transaction a lot. I will introduce later. That is another solution. Database use such a transaction model. Because of that, when you are using database, you need to check whether database support multiple transaction. Okay? If database is a single user, the system, it doesn't require transaction module. Otherwise, it requires. So this is a race condition. So we need to address such a problem. So to do that, operating system consider so this is the thread, the sequence of instruction of the process. Then, if any part of the process, the access the shared data, this group of instruction is called the critical section. Like for example, in this case, the previous case, I equal 5. This is a shared data. If the system would like to access this shared data, this is called the critical section. Then, before the critical section, the instruction code before the thread enter the critical section, this is called the entry section. Then when we exit this one, this is called the exit section. And the others are remainder section. So operating system divide any instruction code, the process, the 4 parts. One is entry section, and the second, the critical section and exit section, and the others are remainder section. So if the process access only local variable, that is just the remainder section. But when the program would like to access the shared data or any shared resource, this is called the critical section. So to access the critical section, we have something before the entry section. Then when a process out of such a critical section, that is called the exit section. So operating system consider the thread of instruction by this different section. Then, for example, we have the bathroom. So, bathroom, can you guys share the bathroom toilet bowl? No, definitely not. Only one student can use that. So, that's the shared data. So, if you are using the toilet bowl, that is the critical section. But to use that the toilet bowl, you need to get the key, right? So, you need to find the key. There is a key, then take it. This taking the key part is entry section. Once you are done to use your toilet bowl, you need to back to the admin wherever. So that is the exit. Then your normal life is the remainder section. So what's the problem? What if there are two students outside of the bathroom? So they are competing. You cannot allow both of them. So sometimes there are multiple processes in the entry section. Entry section means I'd like to access, I'd like to use the toilet bowl. How many? If what? It's no problem. Okay, it's not sure there. But if multiples, the many students are waiting, then you need to select one of them. That selection process will be done during the entry section. Also, this exit section is also important. Why? What if?
Because
I do not return. Nobody can use. Right? You should do something. Also, I have a friend, so I can give the key to my friend who are waiting. There may be also one possibility, okay? Or you can just throw away, then they can fight each other. So another, the algorithm for the exit section. So this entry, then use the shared data critical section, then exit. Then the others are called the remainder section. This is called the critical section part. So operating system consider the thread of the instruction process execution by critical section. So the sequence of thread the instruction as entry section, critical section, exit section, and remainder section. You can understand the entry section as the kind of voting, because this is a shared data but cannot be used by the same time. If you allow the multiple process access the critical section same time, it will cause the critical section, the synchronization problem. Okay, so we need to vote. We need to select the one process to enter the critical section. Also, when a process complete the critical section, which means no longer use the shared data, that should do something like the return the key or the select the next process, something like that. So that is called the exit section. Then the other normal. Normal means without accessing any shared data. This is called the remainder section. So operating system consider the thread of the such an instruction as the critical section. This is called the critical section problem. Then problem, this one, entry and exit section. Operating system involved to address the problem of the synchronization issues, the race condition, by adding additional code to the entry section and exit section. Many of the times such a critical section will be managed by what? Kernel. Because it's a shared data. If we are accessing the local variable only, it doesn't matter. But since you are accessing the shared data by multiple, sometimes it can be shared memory that you tested on the communication. Think about the IPC. IPC, you can create the shared memory, then the multiple processes are accessing. So who will control such a shared data? By operating system. Also, it can be something other resources. So many of the time, this critical section will be kernel mode. So kernel mode. So taking. So when a process would like to access such a, this one is not just only variable. It can be memory. It can be any resources. Okay. To do that, this is a really simple problem. This part, not really the simple case. So this is the user code, access the critical section, which means the shared data, and the other code. If operating system recognize that this process I is accessing this shared data, add this entry section code. While turn is equal to save. What does that mean? Turn is the variable by the operating system, and is equal to J is another process. So if currently the toilet bowl is used by J, then it's true. True means what? Cannot get out of this while loop.
No.
So keep waiting. Okay? But if the process J, return the key. So which means turn is not J. This is a false, right?
Yeah.
Then false means out of
Go outside.
while loop, then access the critical section. Okay? Then once this one is done, then this process I return the key to what? J. Okay? Then the J, if J is waiting for this one, then can enter the critical section. This is just a simplest example of how operating system use the critical section problem by adding entry section and exit section. Okay? So this is called the critical section problem to solve the synchronization issue. So to do that, solution satisfied with a certain condition. Before this one, think about the toilet bowl again. First, how many user can share the toilet bowl? Only one. Do you want? Nobody wants. So only one user can use the toilet bowl, which means mutual exclusion. The solution should be mutually exclusive, which means only one process can access shared data. If you allow, that will be race condition. It will be messed up. It's not synchronized. So only one user. Okay. So everybody can understand first the requirement of the solution. Second, progress. I will give the 1 minute to understand the definition of this one. Why don't you try to understand? Sometimes it's not simple to understand the textbook definition. Okay, so let me read the definition of the progress requirement. If no process is executing in its critical section, okay, and some processes wish to enter, this is important, some process wish to enter their critical section, then only those processes that are not in remainder section can decide the next one, which means, let's go back to the toilet bowl example. So this is our toilet bowl, like this. So then, currently user A is used this one. Then outside B, C, D is waiting. So some process wishes to enter. So these processes are in the entry section. Okay. There are process E, F, G. They are in the library. It's a normal. Okay? They are in the remainder section. So that once A is done, A has probably exit section. Okay? So then do something like the returning a key and so on. So for example, is this one, this A return the key to E, who is in the library. They are keep waiting, right? Keep waiting. So second, the requirement is only process in the waiting list who are waiting for this toilet bowl will be the decide the next one. So when this process A process return, the key should be one of these. Okay? Then one of these can enter the critical section to use the shared data. Okay? So this is a progress. So progress means eventually, unless this is an infinity waiting, so it's an infinity waiting, which means that eventually one process will be selected. From where? This one, from the entry section. Okay, yes?
What is RC?
RC is the remainder section. Remainder section means normal life. Not trying to use the shared data.
But
okay?
It's currently, once it's in the critical section, it goes to the remainder section? That's the way it's...
Remainder section is just a normal code. Okay?
Yeah, it's
any kind of code, but in part of your code, access the shared data I, for example.
Yeah.
Then operating system had entry section and exit section. This is called the critical section. The others are remainder section. So you don't have to worry about the remainder section in your the synchronization solution. But if you give the key back to the one of the process who are not in entry section, which means remainder section, it will be forever. They are keep waiting.
Yeah, you'll never get it done.
That is the progress. Progress means eventually one of the process will get the key to access the critical section. That makes sense. So third solution, third requirement is, so this waiting time should be bounded. Okay? Bounded. Which means even though user A return the key, so for example, B, C, and A, they are very close to each other. So they give the key each other. So D never get the chance. It's not fair, right? So even though key is returning to the one of the process in the waiting, but if there is a process or processes who never get the chance to get the key, that is not acceptable. So such a waiting time, we cannot avoid the waiting times, but such a waiting time should be bounded. Okay? So in my experience, it's not easy to understand progress and the bounded waiting from the definition. Instead, why don't you think about this one, deadlock free or starvation free? So this algorithm should be deadlock free. What is a deadlock? Waiting each other. Okay? So this one, if the user return the key to the student who are in the library, so this user is waiting, keep waiting, but never be returned to the toilet. Okay? Yes.
But why would that ever happen? It doesn't make sense. Why would?
Yeah, because it doesn't make sense, so we are not going to consider this as the solution. Right? It's a requirement. So I'd like to simplify the meaning of such a requirement for you guys. So should not be happen. Such a returning the key to the remainder section. So
entry section.
yes, that is a reason only process, some process wish to enter the shared data will be selected, considered, not in remainder section. Okay, so you can understand the second requirement progress as the deadlock free. Okay, deadlock free means they are not going to wait for each other. Then starvation free means, so even though you return the key to one of the process, but if you do not give the key to the D, okay, it will be forever starvation. So it's a starvation free the problem. So the toilet bowl, the process, the protocol should satisfy with these three requirements. It's the same thing in the accessing the shared data. So we need to consider these three requirements. Not always these three requirements are satisfied, but we pursue. So what we see the example of that. So as I introduced, there are different types of solution, but we will start from the software solution first. Okay. For your better understanding, as we define the model, producer and consumer, two process case, we will consider two process the case, like the process 1 or process 2, or process I or process J. If we make the two processes case, then we can generalize to the n number of cases. Okay? For your better understanding, I'm going to use the two process case. Actually, it's not the generic, so it will be more complicated. But for your understanding, we can consider two processes. So there are only two students who try to use the toilet bowl. Okay? That's the idea. So then, first time, it's not that easy to understand what's the meaning of this one. Think about that we have two processes, like the process 0 and process 1. Process 0 has a sequence of instructions. Okay, right. Process 1 is a sequence of instructions, right? So each of them is running on the CPU number 0 and CPU number 1. There is a shared data. Okay, this is let's say the memory, shared data. So let's say this is I. So when process 0 would like to read the data I, okay, this is called what? Critical section.
Yep.
So we define, operating system define. To do that, operating system provide what? Entry section and exit section. This is an entry and this is an exit. Similarly, when P1 is accessed the I, then entry and exit, like this. So this algorithm, in addition to it process the thread at the entry and exit section. In this case, entry section is, I don't explain the algorithm yet, just to understand the process mechanism to address the problem of the synchronization. While loop, this is the entry section, and this is the exit section, which means whenever access this one, so at Y, the turn is not 0, and exit is turn is 1. This code will be added by operating system. This code and this code. It's not user code. User code is a thread, like this. Then when the user code process 1 would like to access the critical section, the shared data I, then consider this part as a critical section. When the operating system found the critical section, then add the entry section and X section in between. Okay, same thing. This is the entry section and X section. Then see, what's the solution of this one? So we are going to use the one shared variable ton. So ton is the shared variable. So meaning is, ton is who is using? Who is going to use the shared data? So whose ton is that? So if ton is 0, process 0 is using. And if ton is 1, it's a process 1 that is using. So let's take a look at the entry section. This is for process 0. In case of the process 1, the entry section will be 1. The ton is not 1, like this. Okay? This is an example of process 0. In case of process 1, entry section is like that. Exit section is ton is 0. This is the process 1. The operating system add this code as the entry section for process 0. Process 1 is this. Okay? So let's go over. The first, process 0 would like to enter the critical section, which is read the data I in the shared memory. So operating system realized this is a critical section. So add this code, entry section. So currently ton is 0.
So it won't go in there.
Yeah, so check. Ton is not 0. Is it true or false?
False.
0 is not 0. It's a false. False means
Go
out of while loop. Means process 0 access this one. Once again. So
But why?
at this time nobody use the shared data. Okay? Then this is the initial value, just the default value. And first, the process 0 would like to read the shared data I. So operating system realized this is a critical section problem. Okay? So add this code. While ton is not 0, this is an entry section. So entry section means that we are going to vote who is entering. Okay? So this time ton is 0. 0 is not 0. It's a false. False means out of while loop.
Okay, so the critical section is out of the while loop.
Yes.
On this picture.
To enter the critical section,
Yeah.
we need to. This is not the part of block of the while loop.
Well, because it's indented very.
Okay.
Very much.
Yeah, so you need to
so
see
it's
that
really
this one.
confusing.
Semicolon. It's not block, okay? So let me change it. If you it should be like this.
Yeah.
Okay? So it's a to be out of the while loop. It's a false. So it's a false. So enter the critical section, which means currently process 0 is using tolerable. Okay, shared data. Then this time, at this time, so this in the middle of this time. Okay, same time, the currently ton is still 0. P1 is would like to enter the critical section. Read I. Then add entry section and exit section. Entry section is while ton is not 1, because it's a for process 1 case. This is a process 0 case. So then what happened? Currently ton is 0. Okay? And 0 is not 1. Is it true or false?
True.
True means keep checking. Okay, it's a while loop. Okay, so it's waiting. Then, what happened when process 0 is done? Process 0 is done. So turn is 1. So this one is 1. So then this one is a remainder section. Normal the instruction. But process 1 keep checking, then turn is changed to the 1 is not 1. Is it false or what?
False. So now
It's a true or false. False means out of while loop can enter the critical section with the data I. Okay?
So then it enters and then
Enter
it
the
becomes
critical section
2, right?
Yeah. Then when this one is done, turn is equal to 0. Give the key to other because we have only 2 processes.
Okay.
Yeah, limited. It's a first solution, so limited by the 2 process each other. Okay. This is another view of the algorithm, just exactly the same as this one. This is the shared data turn, and this is the sequence of the instruction of P0. This one is a sequence of process 1. So one of the confused part is the why this one is turn is not 0, but this one is a turn is not 1. Because this is the code assigned by the operating system for process 0. This is a code assigned by the operating system for process 1. Okay, and so we can do the. So actually, basically what? Locking. Give the lock to the one process. So this is one of the solutions. It's a very old and simplest the solution. We are going to check whether this solution satisfies with the 3 requirements of this one. First requirement, mutual exclusion. Is it how many processes can enter the critical section? Only 1, maximum 1, so it's good. However, progress, why is bad?
Because of all the waiting, isn't that bad?
If something happens in the axis section is not turn is equal to 1, it's equal to 2, for example.
It'll never happen again.
Yeah. So it may be in case of multiple processes. So if they do not consider who is waiting, who is not. In case of 2 processes, even 2 process case, if this process is never entered the critical section, so this one would like to enter one more time, but cannot get this one. Why? The algorithm axis section does not consider this part. Okay, so it's not progress. Because of that problem, automatically it can be the not bounded waiting. Forever you can wait, right? Those who are in the entry section can wait forever. So it's one of the simplest algorithm, but it doesn't satisfy the all requirement. But it's a good example to understand how operating system use synchronization solution. Okay. Then to address this is another approach. We use the key part is this one. Actually, this is a key lock. Those who use this one can enter. But we don't know who is waiting. Okay, who need a key? So I need to check every time. So instead, what time is it?
48.
So let me finish this one. So this one is we try to check the 2 process, still 2 process case. So whether we have 2 students who try to access the toilet bowl. Okay. First student, yes or no. Second student, yes or no. If we have the many, yes or no, yes or no. That will be checked by the Boolean data type flag. Okay, so flag 0 means flag 0 false. Flag 1 means none of them would want to access the critical section. None of them want to use the toilet bowl like this one. Okay. So this is a process I. I should change. Process I means so 0 and 1. You can understand 2 processes. So process I, the process 0 is true. Okay.
Yeah.
Then while flag J, another process. It's the same mechanism, but we are using flag. Okay. So then for example, flag true. At that time, flag J is a false.
Yeah, so it doesn't
Check whether other process is a false. False means enter critical section. However, at that time, if this one is true, already used,
and
waiting until this one exit part is make false. I'm done. Okay, I'm done. Then the other process can enter critical section. So only one process can enter. So mutual exclusion is okay. However, progress, what if both of them are true? This one is true, this one is true. No matter what happened before. So nobody can enter they believe each other being used, but actually nobody used. That may happen in multiple process case. Okay, so this one is also that's not satisfied with the progress and the bounded time. Only mutual exclusion. So by combining, the idea of this one is a key. Idea of this one is who is used. Check whether this one used or not. Yes. So first synchronization problem is by combining flag and the time. That is the Pearson solution. This is the solution in the computer science, the synchronization problem that satisfies with all three. So by next class, why don't you try to understand the Pearson solution? Okay. So then we will start from the Pearson solution. That is actually combining these two, key and status. Okay, thank you, and see you next class.